morning to all. So today I will be discussing about the few important questions from ESR spectroscopy. So here the first question, what will be the value of I of chlorine if CCl3 shows 10 lines in the hyperfine structure of its ESR spectrum? As we know, the number of hyperfine lines in the ESR spectrum can be calculated by using the formula, that is 2Ni plus 1. 2Ni plus 1 is given in the question, that is 10 lines, and we know that surrounding 3 chlorine nuclei are involved. So we can write here 2, whereas N is number of chlorine atoms, you can write 3, and I. Here we want to calculate the I value for the chlorine, so which is equals to 10. You can also write 6I is equals to 10 minus 1, which is equals to 9. So I value must be 9 upon 6, so which can be equals to 3 by 2. So here for the spin of the chlorine nucleus can be said to be I value 3 by 2. So option B will be the right answer. So come to the next question. So the number of fine and hyperfine ESR lines expected for octahedron high spin manganese 2 complexes respectively are. So this is manganese. Manganese is a high spin complex. So for the high spin complex, the configuration you can write it as just D5. It is having all 5 unpaired electrons. So we know that the number of fine lines, that means a number of fine lines is always equals to the number of unpaired electrons. So here it is having total 5 unpaired electrons, each contribute half value for the I. So the number of fine lines is always equals to the 5. So here 5, so you can neglect these two options. So out of these two, then again number of hyperfine lines. So the number of hyperfine lines can be calculated by using the formula 2Ni plus 1 multiply with the total number of unpaired electrons. If it is single unpaired electron, then you can just directly calculate 2Ni plus 1, but it is having total 5 unpaired electrons. So the hyperfine lines must be equals to 2Ni plus 1 multiply with total number of unpaired electrons. So here total number of unpaired electrons are 5 and multiplied with 2Ni plus 1. Here manganese is single nuclide is present, and each manganese contribute 5 by 2 spin plus 1. So here the total value 5 multiply with 6. So you will get 30 hyperfine lines. So total number of hyperfine ESR lines are 30 and fine lines are 5. So option A will be the right answer. Come to the next question, that is number of hyperfine lines in the ESR spectrum of the given species is. So they have given this compound structure. So this structure, here the one unpaired electron is present. This one unpaired electron can interact with the unpaired electron hydroids. Here you can observe these two are actually chemically equivalent. So that was the reason you can say these 6 hydrogens are one category and the remaining 2 hydrogens are on one category. So you can represent these two are AA and these 6 are considered as another category BB. So this unpaired electron can interact with 2 different hydrogens. So that is the reason the one unpaired electron will interact with 2 equivalent hydrogen, and at the same time it can also interact with 6 different equivalent hydroids. So total number of hyperfine spectral lines can be calculated by using the formula, that is 2NaI plus 1. Na means one category of hydrogens multiply with 2NbI plus 1. So here 2Na, this kind of hydrogens, how many are there? Only 2 were there, and hydrogen spin is half, I value plus 1. And these methyls, how many are there? Total 2 methyls which are equivalent. Total 6 hydrogens are of same category. So 2 multiply with 6, each hydrogen contribute half spin plus 1. So here the total value will get 3 multiply with 7. So you will get the value 21. So option C will be the right answer. Give the number of ESR spectral lines of a dithiazolyl radical. So this is our dithiazolyl radical. In this radical unpaired electron can show ESR signal of this radical will give hyperfine splitting by 2 nitrogens differently. This is 1 nitrogen you can consider, this is 1 nitrogen, because both nitrogens are having unpaired electron, and also it can splitted hyperfine splitting by 3 hydrogens also at the same time. So overall the multiplicity of this compound can be calculated as, so here 2N1, so this is one category you consider, 2N1I plus 1 This is the first nitrogen, and another to N2I plus 1. These two consider as NB, second category of nitrogen, multiplied to N. So here we are considering all three hydrogens of methyl, I plus 1. As we know, the I value for the nitrogen has given as 1. So we need to remember this value. So for the nitrogen, first nitrogen, it has given, how many are there? 1 type only there. I value is 1 for nitrogen. And here also same, only one nitrogen is present, the I value consider as 1. And here the methyl, 3 hydrogens are there, and each hydrogen is contributing half I value. So you will get total, so 3, 3, 4. So you will get quadruplet of triplet. That means total you will get the value of 27. So option B is the right answer. This question asked in the assistant professor examination recently. And next question is the number of hyperfine lines in the ESR spectrum of given free radicals. So they have given the free radical, this one. So this molecule closely, this species contains two types of spin active nuclei. That is, this is one spin active nuclei and this is one spin active nuclei. The two different spin active nitrogens are present. At the same time, this molecule is having 4 types of equivalent hydrogens. You can consider these two are equivalent and these two are equivalent, and at the same time these two are also equivalent, these two. So total how many categories are there? 1, 2, 3, 4. 4 types of equivalent hydrogens are also present. So that is the reason these are 4 types of equivalent hydrogens. The total number of hyperfine lines can be calculated to N1I plus 1. This N1 corresponds to the first category of hydrogen, to N2I plus 1, second category of nitrogen, to N3I plus 1. This is corresponds to the third category of hydrogen, and to N4, that is considered as N4I plus 1. This is the fourth category of hydrogen. Apart from that, it also having the nitrogens, that is considering it as these two nitrogens. But here you notice these two hydrogens are chemically not different. They are having both equally chemical environment. So these two together you can consider as one category. So you can write it as 2N nitrogen I plus 1. So if you substitute all the values, so how many N1 are there? 2. So 2 multiply with 2, half plus 1. So you will get the value of 3. Here also you will get the value of 3. 3. Here also you will get the value of 3. Finally here you will get the value, whereas 2 nitrogens are 2 are present, I is 1 plus 1. So you will get the value of 5. So overall you will get the value 3 multiplied with 3, and which is further multiplied with 3 4 times, which further multiplied with 5. Multiply 3, 3, 3, 3 and multiply with 5. You will get the total value 405. So you will get how many lines in the ESR spectrum? Total 405. Another very important question they have asked in the set examination. So here, which one of the following will not show ESR spectrum? First of all, we should know basic principle of ESR spectrum. Any system to exhibit ESR spectrum, it should contain a 1 unpaired electron or more than 1 unpaired electron. Then only it can interact with electromagnetic radiation, and thus ESR spectroscopy will be arise, right? So here, first thing we have to notice whether these molecules are having unpaired electron or not. First is benzene anion. So benzene anion used to have 7 electrons. Out of 7, 3 were in the paired and 1 is unpaired. So this can be ESR active. Whereas cyclopentadienyl cation. Cyclopentadienyl cation, total it is having 5 electrons. Out of 5, it is in the cationic state, only 4 will be there. If you fill all 4 in the MO diagram, you will get there is a presence of 2 unpaired electrons. So this molecule also shows ESR spectrum. So come to the cyclopentadienyl anion. Normally cyclopentadiene 5 electron, anion means 1 more, so 6 electrons. All 6, if you see the MO diagram, all 6 is arranged in bonding molecular orbitals only. So there is no unpaired electron, so it is ESR inactive. So option will be, right option is A and B both. So that is A, benzene, which do not show ESR spectrum, sorry. So do not show means benzene can't show ESR spectrum. And this cyclopentadienyl anion also do not show ESR spectrum because there is a no unpaired electron present. And there is another concept here you need to remember. For showing ESR spectrum, the compound must be paramagnetic, and here paramagnetic substances are you can classify in two types. One is a stable paramagnetic substances, another is unstable paramagnetic substances. So stable means what? Those substances, by looking you can't say whether it is having unpaired electron. Just by drawing a MO diagram only you will understand that there is a unpaired electrons are present. So these molecules you need to remember, NO, NO2, these molecules by looking you cannot say that unpaired electron, but still it is having unpaired electron which can be confirmed by MO diagrams. Now unstable paramagnetic substances, so like majority of the free radicals are coming under this category. So all the unstable free radicals shows a ESR spectrum, and in that also ESR spectrum, to study ESR spectrum, it should have a lifetime must be greater than 10 to the power of minus 6 seconds. That means the radical lifetime must be 10 to the power of minus 6 seconds. What does mean by radical lifetime? That means to undergo excitation and come out, it requires some time. So it requires greater than 10 to the power of minus 6 seconds. Then only the radical lifetime, if it is more, then only it can absorb the electromagnetic radiation, then only it can exhibit the ESR spectrum. So thanks for watching this video.